So it's time to introduce the Kalman filter. The Kalman filter is a method of tracking linear dynamical systems with Gaussian noise. And what's really cool is both the predicted states and the corrected states are Gaussians, right? So you're only maintaining the mean and the covariance of your state in order to run your filter. And also the calculations are very straightforward. I'm not even going to derive the equations here. We will get some intuitions, but you can show that it's a relatively straightforward manipulation of these linear matrices. So in pictures, the Kalman filter can be described as the following. All right, you start off in the blue here is at the top left. That's your prior belief, right? So let's suppose we have some density. Now, what kind of shape is it? It's a Gaussian. Why? Because this is a Kalman filter. Okay, Kalman filters are built on Gaussians. You want to have a non-Gaussian? Too bad. This is a Kalman filter. Things are Gaussians. We'll do some other little stuff later. For now, everything's. So the first thing that happens is, in this picture, is referred to as a deterministic shift. Remember when we multiply it by that linear system? So basically, that's the part that you know what happens. And that's shown here in green, where the Gaussian bump has just slid over to the right. So if I'm a Gaussian bump, which I've been accused of on a variety of times, the first thing that happens is I slide over to my right. That would be your left. Now, Megan is wondering, should I move the camera? I don't know what this guy's going to do. I'm going to come back in a minute. All right. Anyway, so the first thing we do is we slide. And we know that's the deterministic part. Then comes the part that's referred to in this picture, and I left it in here because I think it's a cool way of thinking about it, stochastic diffusion. But it's basically the addition of noise. And this is referred to the process noise. So now we've done two things. We've deterministically stepped one way, and we've grown a little fatter. Both problems. Anyway, the idea is when I'm taking a step forward in time, I use the part that I know. I think I was moving, 3 meters per second, and it's a second later, so I think I've moved 3. But I also know that I'm not perfect in my knowledge, right? That's never my problem. That's somebody else. But no. Anyway, I know I'm not perfect in my knowledge, so therefore, over here, my variance is wider. Okay, so I've now expanded my uncertainty. Then what happens is I take a measurement, and that's shown here as z. Okay, so I take some measurement, and what happens is if you take a look at the density in the blue here, you'll notice that it has shifted back a little bit based upon the z, and it has also gotten narrower. Okay, it's very important to think about this in the Kalman sense, and we're going to do more of this in a minute, right? We shift, expand, measure, shrink. Okay? Actually, shift, expand, measure, correct, shrink. That shrinkage happens because whenever you take a measurement, you're getting new information. New information can only reduce your uncertainty. That's going to come back in a minute to be a little strange.